Welcome to Robotics Lecture 11. This is your Professor Atif Fareed Muhammad. We will discuss the linear control of manipulators, feedback and closed loop control, second order linear systems, control of second order systems, disturbance, rejection, modeling and control of a single joint. Last but not the least, we will also discuss architecture of an industrial robot controller. Let's dive into the details. The linear control of manipulators, a robotic arm in an automotive assembly line using linear control to place parts precisely. Let's dig deep into this in a little bit more depth. Linear control of manipulators is a fundamental aspect of robotics that focuses on the regulation and guidance of robotic arms to achieve precise movements and positioning. This control strategy typically employs linear feedback techniques to maintain the desired trajectory and stability of the manipulator. By utilizing linear control theories such as proportional integral derivative or PID, control engineers can effectively manage the dynamics of robotic systems. These methods rely on linear approximation of the system's behavior around operating points, permitting for the design of controllers that can handle small deviations and ensure accurate performance. Simplicity and robustness of linear control makes it a popular choice for many industrial applications where manipulators are required to perform repetitive tasks with high accuracy. In the context of manipulators, linear control systems are often implemented to manage both the position and velocity of the end effector. This involves the use of sensors and actuators that provide real-time data to the controller, enabling it to make continuous adjustments. One of the key advantages of linear control is its ability to be easily tuned and adapted to different types of manipulators and tasks. However, it is important to note that linear control may have limitations when dealing with highly nonlinear systems or when large deviations from the operating point occur. In such cases, more advanced control strategies such as adaptive or nonlinear control may be necessary. Despite these limitations, linear control remains a cornerstone in the field of robotics, providing a reliable and efficient means of achieving precise manipulations in various industrial and research settings. Manipulator dynamics, simplifying the dynamics of two-link planar robot arm to design a linear controller. Let's look into this with an example. One example of manipulator dynamics can be observed in the operation of a robotic arm used in automotive manufacturing. Consider a 6-degree of freedom DOF robotic arm tasked with welding parts of a car body. The dynamics of this manipulator involve complex interactions between its joints and links as it moves through space. Each joint, whether rotational or prismatic, contributes to the overall motion and must be precisely controlled to ensure accurate positioning and smooth operation. The dynamics are governed by the equation of motion, which account for the inertial properties of the links, the effects of gravity, and the forces and torques exerted by the actuators. These equations are typically derived using Langmuir and Lagrange's formulation or Newton-Euler methods, providing a comprehensive model in the system's behavior. That is the language of mathematics. In this scenario, the robotic arm must accelerate and decelerate smoothly to follow a predefined path while maintaining the correct orientation for welding. The dynamic model helps in designing control algorithms that compensate for disturbances and ensure stability. For instance, as the arm moves, the changing configuration affects the center of mass and the inertial forces acting on each joint. Advanced control techniques such as computed torque control or adaptive control may be employed to handle these nonlinear dynamics effectively. By accurately modeling and controlling the manipulator dynamics, a robotic arm can perform precise and repeatable tasks, enhancing productivity and quality in the manufacturing process. This example highlights the importance of understanding and managing manipulator dynamics in achieving high performance robotic systems. Linear control techniques, the proportional integral derivative PID control, we have discussed this in quite depth. State space representations and control, we also looked into that in our last example. Transfer function models are applied when we are working with these algorithms using PID control to maintain the position of a robotic welding torch is another example that we can look into. A thermostat using feedback control to maintain room temperature. That's feedback and closed loop control. Let's look into this in a little bit more depth. An example of feedback and closed loop control can be seen in the operation of a home thermostat system. As mentioned earlier, in this system, the thermostat acts as a controller, continuously monitoring the room temperature through a sensor. The desired temperature or set point is set by the user. The thermostat compares the actual room temperature with the set point and generates an error signal if there is a discrepancy. This error signal is then used to activate the heating or cooling system to adjust the room temperature accordingly. As the room temperature approaches the set point, the error signal diminishes and the thermostat reduces the activation of the heating or cooling system. This continuous loop of feedback and adjustment ensures that the room temperature remains close to the desired set point. Providing a comfortable environment, the closed loop control system effectively maintains stability and accuracy by constantly correcting any deviations from the set point, demonstrating the principles of feedback control in the practical application. The components of feedback control, as discussed in the previous example, an infrared sensor detecting the position of an object on a conveyor belt and adjusting the belt speed accordingly is another example for you to think about. Performance matrix: stability, accuracy, and precision, response time and steady state error, disturbance rejection and robustness, evaluating the performance of a drone's altitude control system under wind disturbances is an example of all the earlier mentioned. Modeling the suspension system of a car as a second order system. Technically, this is a second order linear system, and let's look into this in a little bit more depth. In the suspension system of a car can be effectively modeled as a second order linear system to analyze and design its dynamic behavior. In this model, the car's body is represented as a mass, while the suspension and the tires are modeled as springs and dampers. The system's motion is typically described by the second order differential equation that accounts for the inertial forces of the mass, the elastic forces of the springs, and the damping forces of the shock absorbers. Key parameters in this model include the mass of the car, the spring constant of the suspension, and the damping coefficient of the shock absorbers. By analyzing this second order system, engineers can determine important characteristics such as the natural frequency, damping ratio, and response to the road disturbances. This modeling approach helps in designing suspension systems that provide a smooth ride, minimize vibrations, and ensure passenger comfort and vehicle stability. The system response, natural frequency, and damping ratio, as discussed earlier, overdamped, critically damped, and underdamped responses, time domain specifications, and the example comes analyzing the response of a door closer mechanism to determine the appropriate damping. Frequency domain analysis. Let's look into this with an example. Frequency domain analysis is a powerful technique used in engineering and signal processing to study the behavior of systems and signals in terms of their frequency components. Unlike time domain analysis, which examines how a signal changes over time, frequency domain analysis focuses on the signal constituent frequencies and their magnitudes and phases. This approach is particularly useful for understanding how systems respond to different frequency inputs, identifying resonant frequencies, and designing filters. By converting time domain signals into the frequency domain using mathematical tools such as the Fourier transform or Laplace transform, engineers can gain insights into the system's frequency response, stability, and performance characteristics. Frequency domain analysis is widely applied in various fields, including communications, control systems, audio processing, and vibrations analysis, enabling the design and optimization of systems for specific frequency related requirements. The control of second order system, the tuning a PID controller for a robotic arm to achieve optimal performance in picking and placing tasks is another example. Advanced control techniques, the lead lag compensators, root locus method, state feedback control. The example is implementing a lead lag compensator to improve the stability of an aircraft control system. Introduction to disturbance rejection. Let's look into this with one example in more depth. A ship's autopilot system is designed to reject wave-induced disturbances and maintain a steady course, ensuring safe and efficient navigation. The system utilizes advanced control algorithms and sensors to continuously monitor the ship's heading and environmental conditions. When waves exert forces on the ship's hull, causing deviations from the desired course, the autopilot system detects these disturbances through gyroscopes and other navigational instruments. The control algorithms then compute corrective actions, adjusting the rudder and propulsion system to counteract the effects of the waves. By employing feedback control mechanisms, the autopilot system can make real-time adjustments to maintain the ship's intended trajectory. The capability is crucial for reducing fuel consumption, minimizing wear to the vessel, and enhancing overall voyage safety, particularly in rough sea conditions. The autopilot ability to reject disturbances and maintain course stability underscores the importance of robust control systems in maritime operations. Techniques for disturbance rejection, the feed-forward control, robust control techniques, adaptive control methods, using feed-forward control in a printing press to compensate for paper thickness and variations is another good example for you to think about. Modeling and control of a single joint, designing control systems for the elbow joint of a humanoid robot. Let's look into this in more depth. Designing a control system for the elbow joint of a humanoid robot involves a multifaceted approach that integrates mechanics, electronics, and control theory. The elbow joint, which is crucial for the robot's arm movement and manipulation tasks, requires precise control to achieve smooth and accurate motion. The first step in the design process is to model the dynamics of the elbow joint, taking into account factors such as the mass of the forearm and any payload, the inertia of the joint, and the friction characteristics. This dynamic model serves as foundation for developing control algorithms that can regulate the joint's position, velocity, and torque. Sensors such as encoders and torque sensors are essential components that provide real-time feedback on the joint state, enabling the control system to make continuous adjustments. Once the dynamic control is established, the next step is to select an appropriate control strategy for the elbow joint. Common control techniques include proportional integral derivative, as mentioned earlier, the PID control, which is widely used for its simplicity and effectiveness in handling linear systems. For more advanced application, adaptive control or model predictive control may be employed to handle non-linearities and uncertainties in the system. The control system must also incorporate safety mechanisms to prevent excessive force or movements that could cause damage to the robot or its surroundings. Additionally, a control system should be designed with flexibility in mind, permitting for easy tuning and adaptation to different tasks and by environments. By carefully designing and implementing the control systems, the elbow joint of a humanoid robot can achieve precise and reliable performance, enhancing the robot's overall capabilities in various applications. The control architecture of a robotic printing system in a car manufacturing plant is also an area that I suggest you to look into quite depth. You can look into Google Scholar or IEEE Explore to learn more on the area of the industrial robot controller and the architecture associated with this. Hopefully this lecture has given you something decent to ponder upon. So I wish you best. Happy learning. See you in the next lecture.